Swayam Prabha. Digital India. Educated India.
So as we stopped last week, that the deformation is related to strain. So before to go into deformation, we have to first define what is a solid body. So let's assume this is a undeformed three-dimensional body. Now, what is three-dimensional body? You have done in your mechanics class a beam. A beam is a body. A column is a body. Your chair is a body. Your table, everything. What you see the solid. A tree is a body. Now, everything we call a solid body, but with some additional thing. Now, what is that additional? Now, there will be somewhere this body is fixed, or we know the displacement, which is our known displacement. Let's say U star is the known displacement, which may be 0. So I know the displacement at some boundary in this body. There may be some force which is acting on the body, which is concentrated force. There may be some force or the pressure or traction, which I already defined, is acting in another boundary. Okay, just like in a beam in a library book or in a almirah, we keep the books on the rack. So those are basically distributed load. So there is a distributed load, and also this body may have in its own weight. So all these things are applied, all these forces are applied in this body and with a known displacement here. Now, if this body is deformable, okay, deformable, then what will happen? The displacement or deformation will occur in this body at every point. Now, let's say this becomes something like, because this is fixed here, so this body become like this. So then we call it a deformable body. Now, in your mechanics class, they told you rigid body, right? The rigid body meaning there is no deformation allowed. Okay, you are applying load, you are applying all kind of its weight, its own weight, or a distributed load, but it is not deformed. But in a deformable body situation, the body will deform and will have a displacement. So this point may shifted somewhere here. Okay, and this has shifted here. So then we will call it a deformable body. And if it is a 2D, then we are seeing if there is a X and Y coordinate we have defined, then there will be a, you can see there is a X direction displacement we normally call U, and there is a Y direction displacement we normally call V. And interestingly, this displacement is not same at every point. They are different. So if you take another point here, this may have displaced some around here. So displacement U and V are completely different. So the solid mechanics like to find out those displacements. Okay, that is what is happening at every point. Now I rub it a little bit, and because we are going to use this. Oops, my original thing gone. Okay, let's say this is my undeformed. Now this is the XY coordinate, and after deformation, I have shown you inside, but if I show you inside, I cannot draw properly. So I am showing that deformed body somewhere on outside. But mind that this is basically this should be inside, okay? But for sake of clarity, I have drawn it outside. Let's also assume there is a there is a line P and Q, and we knew the coordinate XY, and this one is very near to P. So I define X plus delta X or dx and Y plus dx, dy. This is the coordinate of Q. What it means is why I have given dx dy, that is they are very near, okay? They are not far off. You remember that strain we defined, that del L, did we define strain last time or maybe not? Okay. So we have defined strain, right? Yes or no?
No, sir.
No, not yet. Okay. So we'll define the strain after this. So there is a P and Q, and the same thing in the deformed body. Let's say this is P star and Q star, and this is the same line in the deformed body is like that. Now this coordinate here, I will write X star and Y star. I will define what is that star, and this will be X star plus dx star and Y star plus dy star, something like that. Okay. Now what is the strain? Now the linear strain, which normally happens because of the normal load. Oops, what happened here? 1 minute. Because of the normal load, let's say some sigma here, and this one will deform, and this one will become like this. So if the original length is L, and because of this, if this is delta L, and due to this normal stress, normal meaning it is acting normally on that. So we say the strain is, delta L by L. This definition you probably know from your earlier classes. But actually there is a restriction to this L, because if this L becomes this big, then the linearity is lost. Linearity among this del L by L, because it may start to buckle. Okay, it may start to buckle like this, and as a result you will lose the linearity, and then that definition of classical strain will be lost. That's why in this we write limit L tends to 0. This is basically the normal strain. Okay, this is the classical definition of normal strain. Now if I go to the strain in shear direction, let me delete that. I think if you have copied, it is fine, or I'm deleting this. Now for a shear strain, you see this is the body, sorry, this is that my element, and you remember our shear stress like that. This is the rock mechanics positive. Now because of this stress, let's say there is no normal stress acting on this element. So because of this shear stress, how it is going to change? It is going to change like that. So the shape is changed. Now, if this is how it is changing, then how do I define the shear strain? So the classical definition, you note it down. If there is a right angle element, okay, and because of some shearing, this has changed like this, then shear strain is, this is delta theta 1 and this is delta theta 2. So we write gamma xy. If this is xy plane, this will be delta theta 1 plus delta theta 2, measured in radian, not in degree. So this become the shear strain of this red one, this right angle. This is how shear strain is defined. Now for this condition where there is a, we call it a pure shear, when there is no normal stress is applied, although pure shear definition is something else in 3D, but in 2D you may assume that there is no normal stress, just the shear stress is acting. And in that case, delta theta 1 and delta theta 2 is the same thing. They will be same. And then this gamma xy become 2 times of delta theta. Okay. And that 2 has some implication, you will know later on. Why it is 2. Now, what will be the sign? See, for a normal strain, whatever the sign of that normal stress, if it is compressive, then that strain will also be compressive. And in rock mechanics, compressive we normally consider positive, so this will be positive strain. And if it is tensile, the stress is also negative and the strain will also be negative. Okay. Now, for shear strain, what is the sign convention? Normally, you can say a positive shear strain will cause a positive shear stress will cause a positive shear strain, and a negative one will cause the negative shear strain. Or in otherwise, you can assume if a right angle, this red one, its angle become more than 90 degree. Okay, in this case, it is, you see, it is more than 90 degree. Then we normally consider it as a positive. Okay, we normally consider positive, and vice versa. Okay, if the angle become acute, less than 90 degree, then in rock mechanics we will assume it as a negative. So you can see this is our positive configuration in rock mechanics. So this will give us a positive shear strain. But this one, what I have drawn here, this is basically a negative configuration. Okay, in rock mechanics, but this is positive in solid mechanics. So this is how we define the two strain. One is shear strain and another is normal strain. Now we go here. How does this strain relate to deformation? Okay. So as I was telling, there is a, let's say, PQ is a very small segment which is linear, and it become P star Q star. So what I can show you, this and this is displacement. So this may be U, and 1 minute. And this may be V. Now mind that this U is based.
Yeah, I think Professor Dev joined now. Yeah, you can continue this, sir. Sir, your voice is not coming. Maybe you are muted.
Yeah. So we had a power cut. I think we are still recording. So we go. So all of them are here. Nobody left. Okay.
Yes, all of them were there, sir.
Yeah. These days, little bit frequent power cut is happening here, but for short duration though. Anyway, so let us resume. So what I was telling is the displacement of P is become U, which is in P star, and the Q will be accordingly, and in Y direction it is V. Now it's basically U is a function of X and Y. Remember that. This is a function of X and Y. So what it means is at every point this U and as well as V will be different. Okay.
Excuse me, sir.
Can you please share a whiteboard?
Yeah, the whiteboard.
Yes, sir.
Whiteboard what?
The screen hasn't been
So
shared
you
It is
are
yet.
not
not
visible.
sharing.
Oh, it is not visible. Okay. Okay. Now you're saying?
Yes, sir.
Yeah. So I was telling you that U is basically
Yes, sir.
function of X and Y, similarly V. And in this case, this X star is basically X plus U, and Y star, sorry, I'm sorry. Yeah, right. Y star is Y plus V. Okay. This is what is the definition of X star and Y star. Means X star is X plus that displacement because it is shifted in X direction, and Y star is shifted by V amount, which is also a function of X and Y, and that is added to Y. So this is the definition of whatever the deformation is happening here. Okay, and you are seeing it is not constant. It may be constant for certain body and certain load type, but actually it is not constant at every point. They are varying with X, Y in 2D, in X, Y, Z in 3D. Okay. So under this condition, what is strain in 2D? Now I am talking about 2D. A 2D, the strain is defined as if there is a plate, how does it deform by both normal and shear stresses? So it may deform something like this. Okay, so now this, that means its area has changed, and that area has changed because of the deformation at every point. So in this case we will define as what will be our area. The one area, the deformed area, is P star Q star whole square. Because it's a very small, we are assuming like that, and PQ whole star means we are taking the square of that. Now actually when we do, it is basically some dx and dy we multiply in a cross product, but we do not have to go to that detail in here. In solid mechanics, they may tell you that also. But in our case, if we just assume that what happens to his area and that difference in area, that is basically give us the measures of strain in 2D. In 3D is the difference in the volume which gives us the measures of strain in 3D. In there, they do the triple scalar product, you know, A cross B dot C, and here we do only A cross B, you know. So if you are in the vector space. Now this is related to something what we call Exx dx square plus Eyy dy square and plus something we call, sorry, I write with Exy dx dy. This is related to this. Now these Ex, Ey, Eyy and Ex is basically the measures of strain. Okay, so you can see this is in the x direction, this is in the y direction, and this is the hearing dx dy, both how it has changed. Now how do I find this Exx, Eyy and Exy? How do I find from here? So PQ is very easy. PQ is dx square plus dy square. So let me just write, I delete this part. Okay, I write here. So PQ square rather is dx square plus dy square. But what is this? This is P star Q star, this whole square is this square plus dy star square, right? So this is what is the difference. Now what is dx star? Can anybody tell me how do I find that using this relationship? You have done it in your class 12 also, I guess. How do you calculate the differential? Dx star is the differential. So this will be, if it is 1D, you know, the differential, let's say y equals to x square, then what is dy? If y equals to x square, what is dy? Can anybody tell me?
2x dx.
2x dx. Now let's say z is a function of both x and y. Then in this case it is the x star is function of both x and y, because you see this u is function of both x and y. Then how do you do?
Partial differential.
Partial differential. Okay.
We will assume one constant and differentiate with respect to another.
Exactly.
Or
So
we can use chain rule.
yes. So you know that. So we will write dx star by dx plus dx star del x star del y dy, right? Okay. So this one will become what? 1 plus del u del x dx. I'm just writing one, other one you can write. And this one will become y del u by del y dy, right? Because x and y are independent. So similarly, you can write the other one. Let me delete that. Similarly, you will be able to write dy star. This will be del v del x dx plus 1 plus del v del y dy. Okay. So now you have to square it. Now you can see this entire thing and this thing, you have to square it and then add, then subtract from here. So you will see there will be term dx whole square, dy whole square, and there will be dx dy. Those two terms will come. Okay, that's why I have written it like that way. Exs uyy and exy. So if you all of you got the book, or you are not looking for the book. See, the many things will be done from the book. So if it is available in your area, you can get it, or you can order it also through online. Now, I directly write because you can now do it, or it is given in the book. That's why I'm not deriving it directly. I'm just writing what is exx. This becomes half of, because that half term we normally take. This is the component attached with dx square. Okay, this is the component attached with that. So this is 1 plus del u del x, this whole square, plus del v del x whole square minus 1. It comes something like this. And this, if you do, this become del u del x plus a component half of del u del x whole square plus del v del x whole square. This is becoming the definition of string in x direction. Okay. Now, you see there are two parts here. This is the linear component. Okay. This is the linear part and this is the non-linear part. Okay. You know, in differential equation, this will be non-linear part. Now, you think about our material. So this is what this E mean is called the engineering stream. Okay. Now this has a linear component as well as a non-linear component. Now the material what we use, let's say the rock, or let's assume very brittle nature of some solid. Even you can say copper is basically more or less ductile, but there are many metal which is also brittle, very hard. Let's say steel. Okay, and those, if you see the amount or the value of this is in the order of 10 to the power minus 3 to 10 to the power minus 5 or minus even 6 also. It depends. Minus 6 will be pretty low, but it is in that order. Okay, this is a strain. What is that? This is the gradient of the deformation u in x direction, correct? This is the slope of u, how the u is varying in x direction. And if you take the slope, keeping y constant, this. So this value is very low. When you will test in the laboratory, you will see this value is very, very low. In the order of 10 to the power minus 3 minus 4. When we test a 100 millimeter rock sample, I'll show you one, just a piece of rock. When you test a piece of rock of a cylindrical shape, if it is a 110 millimeter, let's say, is length, before it breaks due to loading, it hardly goes, its deformation hardly happens 1 millimeter. It's sometimes 0.7 millimeter, sometimes 0.8 millimeter. So you can see 0.8 divided by 110, it is in the order of 10 to the power minus 3. So the value is very low. Now if I square it, it is 10 to the power minus 6. So when you are adding 10 to the power minus 3 to 10 to the power minus 6, so this more or less become 0 for our type of material. So that's why in rock mechanics, we hardly use this component. Okay, so ours is mostly we use this, only the linear part, and that's why we change the symbol also, and we call it epsilon xx, and this is the normal strain. So exx become the epsilon xx, is called Cauchy strain, or Cauchy's infinitesimal strain, very little strain. Okay, that's why it's called, or the symbol also changed to epsilon, not E. E is the engineering strain, epsilon is the Cauchy strain, or the only linear part of it. Similarly, epsilon YY will be del V by del Y, and gamma XY, which is the shear strain, this will be del U del Y plus del V del X. Okay, this is in 2D. In 3D, there will be another component of epsilon ZZ, that will be del W by del Z, something like that. So that will be another 3 tensor will come. So now we have one tensor in X direction. These two are normal tensor, and this is the shear tensor for strain. This one is related to sigma xx. This one is related to sigma yy, and this one is related to tau xy. Okay. This is how the strain and stress, the corresponding strain and corresponding stress are there. So this is the relationship between deformation and the strain. Now you may ask, sir, then what is the purpose of this one? Well, this also has a lot of purpose depending on material. Let's say we are using a material, the rubber type material, where the deformation is not so low. Maybe deformation is almost 50%. You can deform a rubber type material almost 50%, and then this nonlinear time cannot be ignored. So that time we have to use it. Even in rock mechanics also, in some problem we use it. Very soft material we are dealing with, and that time we use this nonlinear strain. We also call it geometric strain. Okay. So this is how the relationship between the strain and displacement. Now, before I proceed further, I'm going to load another file or share another file to you, so that you know how do you measure the strain. Okay, and let me share that one. If it allow me to share both the file together, it will be good. Let me just check whether I can share another file. maybe not. Stop sharing. So I can share one file at a time. Are you able to see this file?
Yes, sir.
Yes,
Okay.
sir.
Okay. Wait a minute. Let me share is in a different mode. Okay, you are able to see. Okay, great. So now what is there is how do I make it big? Well, let me share through this window. I think then I will be able to make it big. Yeah, this is much better. Where did you go? Yeah. So you are able to see this, right? So you can see here, this one is a strain gauge. You are able to see this. There is one strain gauge written and strain rosette written. You are seeing that, right?
Yes, sir.
Okay. So now this is strain gauge is the measurement of strain. This is basically nothing but a resistance. You have studied in your electrical technology. It's a, you can see very thin wires. Okay, you will be using this strain gauge and you will be measuring the strain in the lab. It's a basically thin wire made as a coil, and then two lead wire comes out. Okay, and this strain gauge, as you know, the since it's a resistance changed with the change of length as well as change of area. Because resistivity of the material is constant, it remains constant. Now, when deformation occurs, because
Okay, so
Sir, someone is muted you.
please unmute yourself.
okay. So now you are able to see.
Yes, sir.
Yeah. So this one, this strain gauge, they are pasted. Let me show you this slide. So they are pasted here. You can see here, or this is a steel pipe. They are pasted in here. And when the pipe length either increases or decreases, or in this case, we are giving load from the top. And when it happens, then its length changes. And as the length changes, its resistance changes. And if the resistance changes, then we can measure its change of resistance using a Wheatstone bridge. You know what is Wheatstone bridge? If it is the balance bridge, then the four resistance remains the same. Now in one place, in one of the resistance, we change it to the strain gauge. We connect, and other three remains the same. Normally, the resistance of the strain gauges are 120 ohm, or 350 ohm, or 1000 ohm. These are the three types of resistance we use. 350 is one of the most common. Even 120 is also common for rock mechanics. Now, the other three also in a Wheatstone bridge, you have studied Wheatstone bridge, right? Wheatstone bridge circuit.
Yes, sir.
Okay, so you know there are four four resistance. So in one of the resistance, we replace that and we put this, and all we put this strain gauge, and all other three remains as a 120 ohm, let's say. So the initially the circuit is balanced and the voltage, the unbalanced voltage is 0. Then as we are loading it, then what happened is the length of this changes, so as the resistance, so we get a delta V in the Wheatstone bridge, and that delta V is related to the change of strain, and the change of strain is related to the deformation. So this is how we measure the strain in by electrical system, and using a simple Wheatstone bridge we can measure it. We can also use 3 strain gauges together. We call it strain rosette. This is like a 45-degree rosette, and schematically we show like this. So at one go we can measure the 3-directional strain. I will come to that later. So this is also 3 strain gauges we put like this. Okay. So is that clear? And this is the box by which it basically inside this the Wheatstone bridge is there already, and when we connect all this, it gives the strain directly here. Okay, in our laboratory we have a box like that, and now this box is connected directly to the computer, and we directly get it to the computer, this strain. Okay, this is how we measure. Now I can give you a food for thought. Can you measure in any other way? Okay, you do not have to answer now, but can we measure the strain in any other way other than this electrical system? Okay, I can give you some hint. You can think mechanical system, you can think of optical system, you know, or any other, maybe radio wave, taking picture. You know, I'm giving you many ideas. You can think about it. You can do some searching. What are the different ways the strain can be measured? Okay, this is one of the most common ways we measure the strain. So now I stop sharing this. You are seeing this, right? What happened to this?
Yes, sir.
One minute. Hmm? Something has happened to my this one. Why it is not coming? Okay. Something is wrong in my digital this thing. It is not coming. Then let me share the other thing. My digital board suddenly stopped working. Let me share the lecture note. Okay. Now the next topic I think I have given you so far is definition of strain. Previously, I gave you the definition of stress. And I also told you how we can measure the strain using strain gauges. We'll do a problem also after we finish this part. Now there is a very important thing in solid mechanics or even mechanics is called transformation. Whether we can transform from some variable from one coordinate system to another coordinate system. This is a very important task. You will not know now, but we face it every day when we go in the field and try to measure something. See, we go there with an intention of measuring in a certain coordinate system. But when we go there, we see it is not possible to measure in that coordinate system at all. And then we have to fall back into another coordinate system. In this case, maybe x dash, y dash. And let's say I'm going to measure a deformation. A deformation is a vector. Let's say this is the OA vector, which had a displacement u in x direction and displacement v in y direction. I thought I will be able to measure it in that coordinate system. But actually, when I went to the field, I said, oh, there is a broken rock there, so I cannot do. So I have to change the coordinate system, x dash, y dash, but I am able to measure that angle between x and x dash. So my question is to you, if I know u and v, then what will be u dash and v dash? I have already solved it here. So the way we transform a vector is very easy. This I also given in that small table. How do we change it? So it's basically OA vector into this u dash direction, which is, let's say, the unit vector is I dash, and my OA is nothing but in the original this thing ui plus vj. So dot I dash. So is u become I dot I dash and v j dot I dash.